Welcome to the 6.3 video, the last video for the general probability section of our course. And on this page you will see the list of the rules we talked about so far. That probability falls between 0 and 1, the probability of a whole sample space is 1, and then the special addition and multiplication rules for special cases. So addition, if things are disjoint, you just add the two probabilities of the two events together, and if two events are independent, to find the probability that both occur, you multiply the two probabilities together, as well as the complement rule, which is the probability of something not happening is equal to 1 minus the probability of that event happening. So to look at that addition rule for disjoint events where you just add the probabilities together, one way to look at this is an event diagram, and if we have these three different events that have no overlap whatsoever, so if B happens, then we know A and C did not happen, we can find the probability that A, B, or C happens by just adding those probabilities together. But what happens if we don't have disjoint events? And for example, A and B overlap. So we have this overlapping area that is A and B. So if that occurs, then you still add the two probabilities together, probability of A and the probability of B, you add those together. But then we've got to subtract out the probability of A and B happening. And that's because in this section here, the probability of A happening includes that section. And then the probability of B happening also includes that section. So in essence, we're double counting it if we just add those two probabilities together. So we have to subtract out one occurrence of A and B, so we're not counting it twice. And that's where this rule comes from. It adds them together and subtracts out their intersection. And then below is the formula written in symbols. So you got your intersection and your intersection and your union here. So that's your union, and this is your intersection symbol for the probability. All right, so let's do an example of how Venn diagrams can kind of help you figure out some probabilities sometimes if there's a lot going on. So we have two people, Deb and Matt. They're waiting to hear if they got promoted. So we'll call one of these circles Deb and one of these circles Matt. So Deb thinks the probability of her getting promoted is 0.7, and Matt thinks his probability is 0.5, and the probability of both of them being promoted is 0.3. So the 0.3 goes in the middle. Now if Deb's whole probability, so if this whole circle, the probability is 0.7, then that means that this section of just Deb getting promoted is 0.4. And the same thing goes for Matt. If this whole probability is 0.5, then the probability of just him being promoted is 0.2. All right, so then if we add these probabilities together, we get 0.9. So that means there's a 0.1 probability that neither of them will get a promotion. So we want the probability that at least one will be promoted. So that would be the probability that one or more of them, or both, basically. So two ways to do it. You could add the probabilities that are in this Venn diagram, and you get 0.9. Or you can do 1 minus probability that neither gets promoted, and you'd also get the 0.9. If you looked at the formula and just did it without a Venn diagram, this is using the P of Deb plus P of Matt minus P of Deb and Matt. Then you'd have the 0.7 plus 0.5 minus the 0.3, which gives you 0.9 as well. So if you just do it straight mathematically formula without a Venn diagram, you get the right answer, but the Venn diagram can give you a little view of what is actually going on within the formula. Then we have conditional probability, and it's a new notation maybe for some of you, and that is what's the probability given that we know something else has happened. So if we get an extra piece of information, does it change the probability? And it's written as P of A given B. So this line you can say as given. So what that means is the probability of A occurring given that we know B has happened. For example, if the probability of getting an ace in any 52 deck of cards is 4 out of 52 or 1/13. If we're dealt 4 cards, one of them is an ace, so our given information is we know an ace has already been dealt. What's the probability our next card is going to be an ace? So now, given that information, we only have 3 aces, and we also have 48 cards. So this new piece of information, so P of, we'll call it ace given already have an ace, is going to be 3 over 48 or 1/16. Now this brings us to a check you can do for independence. So if 2 things are independent, then knowing that extra piece of information that something happened is not going to change the probability. So for example, if knowing I already have an ace is independent of me getting another ace from that one deck of cards, then it shouldn't change the probability, because if I know I have an ace and I'm getting another ace is the same probability, knowing one did not affect the outcome of the other. And the way to check that is to check that probability of an ace is equal to the probability of an ace given you already have one. So if we check these probabilities, 1/13 equals 1/16, that is not true, so not independent. And hopefully that's obvious that if you have a deck of cards that only has 4 aces and you already have one of the aces, the probabilities are going to change. Another way you might see this kind of information is in what's called a contingency table. We talked about these a bit in chapter 4. These are just a way of displaying different categorical data values. And so, for example, if at least one parent completed a college degree, what's the probability their teenager attended college right after high school? So if we read this, so we want to know if one parent at least has a college degree. So all we care about is this table. What is the probability their child attended college right after high school? So attended college, 231. So it's 231 out of 280, which gives us the probability of 0.825. And you would write that as, I wrote it as teen college given parent has a degree. So then, what if we had a different question? A teenager is randomly selected and she did not attend college right after school. What is the probability that at least one of her parents has a college degree? So now we know we selected a teen and they did not attend college right after high school. So we're looking at this row now, and it's 40 parents' degree given that the teen did not attend college is 49 out of 347 or 0.14. You could also, though, look at these tables in terms of proportions, and instead of having total counts. And if we did this and asked the same questions, we're going to get essentially the same answers. You will see on the first one, we have a slightly different answer, but that's because there's rounding going on in the table so that we don't get quite the exact answer as before. And then we could check for independence like I was talking about. So if we want to know if two things are independent is the probability that a teen attends college given their parent has the degree equals the probability of a teen attending college right out of high school. So if these two statements are true, that means that parents having a degree had no effect on whether the teen went to college, and therefore they are independent events. But if we looked at the numbers, probability of a teen attending college is 0.56, and that does not equal the 0.89 of the teen attending college when we know that the parent has a degree. All right. And this is called conditional probability. On your formula sheet, you will see this formula of the probability of B given A, and the denominator is the probability of the event occurring that you know you're being told happened, and then the numerator is the probability of A and B. Now you could rearrange this if you want the general formula for an and by just multiplying over the P of A. And this is where the special case formula comes from for a probability of A and B, where you just multiply the probability of A times the probability of B, because if B is independent of A, that means A had no effect on B, and this would simplify to the probability of B, and that's how you get your special case formula if A and B are independent. But if they're not independent, then it doesn't equal probability of B, and there you have to have this more specific formula. And this is the formal definition for probability of A and B written out nicely as I just described. So this is the general formula you have to use if you don't know that A and B are independent. And finally, I would pause on the screen, make sure you have written down all of the rules for probability, because we'll be using them this chapter, next chapter, and you really need to have a good basic working of these formulas. And this is the end of the video, and I hope it helped.